Imagine an object so dense that light itself, the fastest thing in the universe, can't escape it. That's not science fiction. That's a black hole. And the strangest part is, we calculated it should exist almost 2 centuries before we ever actually saw one. In 1783, the English clergyman John Michell, using ordinary Newtonian physics, proposed that if you compressed a massive enough star into a small enough size, its escape velocity would exceed the speed of light. Light simply wouldn't be able to leave it. The star would become invisible. 133 years later, in 1916, the German physicist Karl Schwarzschild, writing from the front lines of World War I, derived an exact solution to Einstein's field equations describing exactly that kind of object, this time within general relativity. He did it just months before his own death. But an equation is one thing, proof is another. It took 55 more years before, in 1971, astronomers studying the X-ray source Cygnus X1 obtained the first strong evidence that black holes were actually real. So what is a black hole, really? It isn't empty space, and it isn't a hole in the everyday sense. It's a region where gravity is so strong that it warps space-time itself into a literal funnel. The boundary beyond which escape becomes impossible is called the event horizon. Crossing the event horizon is a one-way trip. No signal, no particle, nothing can come back out. And at the very center, if you take classical general relativity literally, lies a singularity, a point where matter's density becomes infinite, and the ordinary laws of physics simply stop working. Where do these objects actually come from? Most often, from the death of massive stars. As long as nuclear fusion is burning in a star's core, radiation pressure keeps it from collapsing. But once the fuel runs out, gravity wins. If the remaining core is massive enough, several times the mass of the Sun, nothing can stop it from collapsing into a black hole. For a long time, black holes were just letters in equations. We could see their influence, in how they whip surrounding gas up to enormous speeds, and how they bend the light of distant stars. But no one had ever seen one directly. That changed in April 2019. The Event Horizon Telescope Collaboration, a global network of 8 radio observatories linked together into a single Earth-sized virtual instrument, released the first ever image of a black hole. It showed the supermassive black hole at the center of the galaxy Messier 87, located 53 million light-years away, with a mass of about 6.5 billion suns. The image showed a bright ring of superheated gas wrapped around a perfectly dark center, almost exactly what the equations had predicted 103 years earlier. Then, in May 2022, the same collaboration released a second image, this time of the black hole at the very center of our own galaxy, Sagittarius A star. It's far closer to us, but it turned out to be even harder to photograph. The gas around it orbits so fast that it visibly changes during the observation itself. It took researchers 5 years and extensive supercomputer simulations to reconstruct a clear image. 2 completely different objects, different sizes, different masses, from entirely different parts of the universe, and they look remarkably alike. Exactly what a black hole should look like if general relativity is correct. From one clergyman's idea in the 18th century to a photograph seen around the world, black holes are a rare case in science where the math turned out to be right long before we had the tools to check it. Which raises the question, what else have we already calculated but haven't been able to see yet? There's also a strange twist waiting, in theory, at the very end of a black hole's life. In 1974, physicist Stephen Hawking showed that once quantum mechanics is factored in, black holes shouldn't be perfectly black after all. Right at the event horizon, quantum effects are predicted to cause a faint stream of particles to leak outward, a process now known as Hawking radiation. Over unimaginably long timescales, this would cause a black hole to slowly lose mass and, in principle, eventually evaporate completely. For a stellar mass black hole, that process would take far longer than the current age of the universe, which is why no one has ever actually detected it directly. It remains one of the most important unconfirmed predictions in modern physics, sitting right at the boundary between general relativity and quantum mechanics. 2 centuries. That's how long it took to go from a single idea, scribbled down by a country clergyman, to an actual photograph of the thing he imagined. Not because the physics was wrong, it wasn't. Just because it took that long for our instruments to catch up with the math. Somewhere out there, right now, there are equations describing things we haven't found yet either. We just don't know which ones, until the day we do.